a couple seconds, and it'll go off. If we call on you, speak loudly. You got to get close to the mic, you got to talk loudly, or otherwise your peers can't hear you. Okay, so everybody get quiet down, now we'll get going. That was just a bit of microphone discipline. So if you're still talking now, you're into the recording. So let's quiet down so we can get going. Okay, so we're talking about milestone 1. And at the very end of last lecture, I told you that the specification of what you're supposed to do is in milestone1.h, m1.h. A couple of students have noticed, hey, this file's not in my repository. That's on purpose. This file is read-only. It's in a shared directory that you can access. Read the milestone handout, it tells you where it is. If you want to look at it, you can navigate to it through your IDE. You can't change it on purpose because this is the specification of what you have to do. This is good practice. You're building an API. The header file should say, what does this API do? How do you use it? That's exactly what you're told in milestone1.h. The detailed specification is in the tests. Well, it's in the instructions that gives more information and hints, and then the more detailed specification are in the unit tests. We're going to talk about unit tests in a lecture or two. There's a quick start guide on Quarkus that I suggest you read. Basically, unit tests are a way of testing the internals of your program. So we're actually going to hook into your program. We're going to test the API you're writing. We're going to test its functionality, and we're going to test its speed. These unit tests, or these tests that you run with ece297 exercise, also automatically run valgrind. So we're going to check that you don't have any memory errors. So if you look inside m1.h, you're going to see a bunch of text like this. I'm not going to go through it all. See the instructions and read the header. In the tutorial this week, we're actually going to show you how to write this function. If you don't get this function right, it means that you were unable to come to the tutorial and transcribe code. So that's not good, right? You should go to the tutorial, and you will definitely know how to write this function. So the function tells you in its comments what should it do. So this particular function, you pass it an intersection ID, and it's going to return a vector of IDs of the street segments that meet at that intersection. Other information that's important here, it says the speed requirement of this function is high. Okay, what does that mean? Well, if you look at the top of the file, you're going to see we define what our speed requirements are. And high basically means we want it as fast as possible. And we believe that to make it this fast, you will have to store some data. Okay, that you cannot make this function fast enough just by calling our lower level API when you ask a question. You're going to actually have to figure some things out ahead of time and store them. Moderate means your code has to be reasonably fast, but we don't think you have to store any data. You can just call our APIs and figure it out. And some of the functions have no speed requirement, which means it's okay to be slow. ece297 exercise has a 5-minute timeout, so if you take more than 5 minutes, you'll fail, but that's a long time. So you can write, code without much regard for speed when the speed requirement is none. Okay, but this particular one, which we'll go over in tutorial again, has to be fast. Okay, so you run ece297 exercise. It's going to run a whole bunch of tests, and it's going to give you a little report. It's even color-coded. So some of the tests are just checking your API does what it should do. Those ones all have the word func in their name for functionality. Some of the tests are going to test that your API is fast enough. So those have perf in the title. How do we set this performance target? So we can't, students sometimes in prior years have asked, well, can you set it based on user behavior? And for a complete program, that can be a very reasonable thing to do. How fast does a game engine have to be in order to get 60 frames per second? And that's a pretty reasonable spec. It's not a reasonable spec here because you're building an API in this milestone, not a complete program. So you can't go out and survey a bunch of users and say, how fast would you like this low-level function to be? Like, they have no idea. So what we do instead is we use an approach that is similar to what the standard template library does. the functions we care about, there are certain functions that we know are you're going to build on, or you could build on in your later milestones and want them to be fast. We also, as a learning objective, want to teach you how to write fast functions. So for those, we basically have worked out what is the best complexity you could get, the big O notation, and you need to write a solution for that function that is of that big O complexity in order to pass our speed tests. So again, this is like STL. STL doesn't know what everybody's going to do with the standard template library, so they just build it to be as fast as possible to get the best big O. That's what you're doing for at least the high speed functions in milestone 1. We do give you some where we just say, you know, you don't have to make these ones fast, but some of them you're going to build on later, they have to be fast. Okay, so what are those big O notations? Well, load map, you're going to see that we always call a function called load map before we call anything else. That's to allow you to do some setup, get some data ready. Load map can be pretty slow. So fundamentally, it has to look at all the data in the city. So it's going to be order n. It can be a little slower even than order n. If it was order n log n, should be fine too. So we give you several seconds for load map. So you can't do anything order n squared. That's going to take a super long time, but you can do quite a bit of work in load map. Load map, the speed requirement is not intended to be really tight. It's just to stop you from doing, well, essentially crazy things like order n squared algorithms, which for the amount of data we have would be extremely slow. The functions that have this requirement of high, so it's maybe half the functions in milestone 1 have a performance requirement of high. You are going to have to store some data, or we believe you'll have to store some data. If you find some way to do it that you didn't store any data, that's fine, but we don't know of such a way. We think you have to store some data. And you're going to have to choose the right data structure. So one of the reasons we've been teaching you STL and talking about the various fundamental data structures, well, milestone 1 needs you to use that skill. So you got to pick for a certain function. What would be if it's got a high performance requirement, how should I store this data in load map so that I can answer questions really quickly? You're basically going to use a data structure that gets you the best, or in some cases doesn't have to be the best, but close to the best big O notation. All right, if you use an inappropriate data structure, you're going to fail, and probably by a lot. The exact way we set the speed tests is we have a reference implementation where we used good data structures. We time it, and then we give you 2.5 times as long as that. We haven't micro-tuned our reference implementation, so we could probably make it a bit faster if we really fine-tuned it. We don't care. So basically, if you use the right data structures and don't do any really strange coding, it'll be fine. You shouldn't have a problem, and you can just run the tests and see. So any questions on that? This is basically considered good software development. Most of the brief specifications in the header file, the detailed specification is in the tests. And that's better than writing a really long document where we say, read all these rules and so on. The milestone 1 instructions are really more going through and giving you helpful tips and background information. But these two things together give you the specification. Okay, so I told you that we're testing you with unit tests. You don't know what that means yet, but we're going to teach you in a couple lectures. The basic idea of a unit test, though, is it can hook right into your program and it can test your functions. So that's what we're doing. So we will always call, this is what ece297 exercise does, we will always call load map first. And we'll pass it the name of the map that we want to open up, and we're going to ask you questions on. So in this example, we're going to ask you some questions on Toronto. The unit test will then ask you all sorts of questions. We've written this code. When you run ece297 exercise, it's connecting you to this code. You can go look at it. These tests are all public. In the milestone 1 handout, it tells you where these tests are. So if you want to go look at them, it's fine. But for example, we have one function you have to write called find closest intersection. And it's passed a latitude, longitude position. Okay, so point on the surface of the Earth, and it has to return an integer. And that integer has to be the ID of the intersection in this city, Toronto, which is closest to that point. In our unit tests, we call your function with some particular position. We already know the answer, right? So we figured out what the answer is, and we check if you return that answer. So you return the right ID, we don't say anything. You return the wrong ID, we print out this is incorrect. and you're going to have to go fix it. We don't test you with just one call of this function. We'll call this function with a bunch of different inputs. We'll check that you get the right answer every time. And then when we've done enough testing, we think it's enough, we stop, and we call close map. Close map is another function that you write, which basically cleans up all your memory. Okay, we check that you have no memory leaks, so you should clean up all your memory. All right, so any questions so far? It's all pretty clear. Okay. Okay, so what do I do in load map? Well, the comment says load anything you want here. So what should I do in load map? Well, at the very minimum, we've given you a couple of lower level APIs. I talked about them on Tuesday. Those APIs need to load their own data. So you gotta make calls to our functions that load their data. That's the absolute minimum of what you gotta do in load map. Okay? And you could say, okay, I'll just do that. And then whatever questions you ask me, I'll work out the answer by making appropriate calls to the low-level API. Because you can't answer all these questions just by calling our lower-level API, in the right way. You might have to write loops and if statements and all sorts of stuff to figure out the right data to return, but you can do it. Okay, so the advantage of doing this is it's what's called stateless. Stateless means, aside from the fact that you asked us to load our data, you don't have any data in your program. You're not keeping any objects around. There's no long-term storage in your program. We ask it a question, it works out the answer, it returns it. That's it. That is actually easier to debug, so that's good. But it's going to be too slow for some calls. So for any of the calls where we say it has a speed requirement of moderate or none, we believe this approach is fine. Well, we're sure this approach is fine because we actually have a reference solution where we used it. So you can do it and you can pass any performance tests we have. But for the ones where we say the performance requirement is high, it's not going to be fast enough, or at least we don't believe it's fast enough. So for those ones, you're going to have to do more. You're going to have to use the second approach, which is that load map does some extra work. It doesn't just load up the data for our low-level APIs, it actually starts calling those APIs in order to create some of its own data structures. You choose what those data structures are. Their whole purpose is to be able to answer questions for these high-performance function calls quickly. So you're going to have to do at least some of two. So my suggestion is we emphasize in this course agile development. We'll talk more about that over the next couple of weeks too. But basically agile development means get something working quickly and measure how well it works and iterate to improve. It's been shown over and over again that people are not that good at planning, especially as you get into really big teams. So the best way to run a project is to track what is working and rapidly iterate to make more things work and to make them work better. So if I want to get this working as quickly as possible, approach 1 is simpler. So I would recommend you get approach 1 working for all your functions. They all work, and they pass the functionality tests, but some of them are going to fail the performance tests. Then those ones that are failing the performance test, you recode them using approach 2. Now you'll find that when you recode them with approach 2, you don't just throw away your older code, right? What you do is you essentially move some of that code or something very similar to that code into load map. You say, this is how I figured out the answer. Instead of figuring out the whole answer when you ask me, I'm going to figure it out in advance and save it. So you don't throw away much code if you do it in the sequence of 2 sub-steps. And as I said, it helps you get something working faster that you can measure, test, and that makes you more productive, makes you more agile. Okay, so I already mentioned this. Load map is also speed tested, so you can't take forever, but you can do a lot. Several seconds, order n algorithms, order n log n algorithms are going to be fine in load map. If you ever write something that is order n squared, that will probably take an hour on the size of data that we're giving you, so that's not going to be okay in load map. Okay, so let me give you an example of this. And I strongly suggest you go to the tutorial. You should go to all the tutorials. It makes us happy. It's good information, but go this week for sure, because we're going to walk through in detail exactly how to solve one of these API functions and how to make it fast. I'm going to go through another one of the functions at a slightly higher level of detail right now, though, too. Okay, so one of the functions you have to write is this one. Its name is find intersections of street, so you'll find this is in m1.h. We pass in an integer, and this integer is actually for the index, the ID of a street, and we're going to return a vector of integers, but these integers are intersection IDs. So we're using our type defs to make this a little more clear. How are we going to do this? Well, the higher level API we gave you, Streets Database API, we can ask a few questions that look relevant. So you again look in the header file for this function, you look in the milestone1 handout, and you'll see that you can ask a street segment, what's your from intersection, what's your to intersection? So we can ask it about the two intersections that belong to it. Every street segment has two intersections, one at each end. A street segment also can be asked, what is the ID of the street you belong to? Now streets don't have much data. Streets cannot answer questions about their intersections. Okay, they can really only answer questions about a few basic things, like what is your name? Okay, so we're going to pass in an ID of a street. Say it's like 150, which might correspond to Yonge Street, and we want you to return to us the IDs of all the intersections along it. Okay, so all these would have IDs, and that's what you should return to us. But this street, there's no API function that we've given you where you can pass in a street ID and ask what are your intersections. It doesn't exist. We never wrote that function. So you can't do it the most straightforward way. So what do you do instead? Well, as I said, street segments do know their intersections, and street segments also know the ID of the street that they belong to. So street segments have all this data. Okay, so, and I'm going to show you the functions that are helpful to you here. So you can ask our API, how many street segments are there in this city? You can ask for any street segment. You can call this function get street segment info. So you can ask for a data structure that corresponds to that street segment. What is in that data structure? Well, there are a few things. It's all documented in the header file, but the things that you need are it has the ID of the from intersection, of the to intersection, and it also has the ID of the street it belongs to. Okay, so this is all you need in order to write that M1 function that I told you about, right? This is the function you're trying to write. So I'm going to put up a timer for, let's see, a couple of minutes, and I want you to do two things. I don't want you to write the detailed code. It's hard to write detailed code just sitting in a classroom. But what I want you to come up with is essentially pseudocode. You know, this is, I'm telling you the menu of functions and data, the structure that you're going to need. I want you to tell me, okay, I'm going to call this, I'm going to have a for loop over this, I'm going to call this, I'm going to store it here. Okay, so I want you to tell me what functions I'm going to call and what the for loops or if statements would be, but you don't have to basically tell me every detail. So I'm going to give you a couple minutes, talk to the people at your table, work out what your strategy is for this, and then one other thing I want you to do is what is the computational complexity of your approach? Okay, that's going to tell us roughly how fast it is so we can figure out if it's going to pass our speed tests. Okay, so take a couple minutes and try to come up with a strategy for that. Okay. If people need another minute, do you want more time or not? Put up your hand if you want more time. Okay? Now put up your hand if you want less time. All right, I'll give you another minute. so I think we're going to start, we'll take up some solutions. So I heard some good ideas on this one. I gave you more time, but it looks like people were making interesting progress on this. Okay, so I am not going to write down super detailed code because I can't do that with a pen on a stylus, but if somebody wanted to buzz in and tell me your overall approach, okay, so what do I mean by overall approach? Well, call this, loop over that, do an if for this, that kind of thing, store this. You don't have to tell me like the exact details, give me the overall structure of what you're going to do. So anybody want to buzz in and take a shot at this? Okay, I will give you chocolate bars if you do a reasonable job of it. So you take a crack at it and you get it kind of like even like 3/4 right. So totally fine. Come up afterwards. All right, well that changed the dynamic. Okay, so this course is like giving a lesson in capitalism, I think, as a side effect. F05, so you should see your mic is green, that means you're on the air. So what do you think? Are you, oh wait a sec, I've muted you. I don't know the system. Yeah, speak loudly, try it again. Let's see. Oh wait, it's E05. Sorry, both of you guys are in. Okay, E05, I selected you. Your mic should be on. So, but I'll come to F05 as well if there's any shortfalls.
Hi, so what we talked about was...
So you got to say it really loud into the mic. And F05 is, they're ready to jump in. So if you want, you can call a friend.
So what we talked about was going from like from the preloaded data of the...
So no preloads yet, okay? So don't worry about making this fast yet. Yeah. Let's just, basically I recommend, it would be good to follow the approach I recommended, which is, let's just get it correct. Don't worry about speed, just tell me the complexity at the end. And then we could talk about how we might make it faster using load map. But it's easier to think about this if we just talk, what do you do to answer this question? Don't worry about speed yet.
Okay, so first of all, we have to find a street segment with the correct street index.
Okay, so you need to find the street segments with that street index. Right, streets can't answer many questions. So you'll find our API has all the information you need, but it's often not in a convenient, often it's not organized in the way you might like. So you can reorganize it. Okay, so a street can't tell you the street segment IDs, so you're saying you got to go through and find the street segments that belong to this street. Is that right? How are you going to do that?
You would just need to find the first one.
Sorry?
You would just need to find one street segment and then go from the intersections.
Oh, okay. So you're saying you're going to loop through, find one street segment that belongs to this street, and then you'll walk up and down it. You'll look at its intersections and find what they're connected to. Is that right?
Yeah.
So you're right. You could do that. I'm not going to write that down for the reason, it's not a bad solution. It's a little more complicated to write though. So I'm going to go for something, there's a somewhat simpler approach than that, which I'm going to go to F0, I'm going to go to F05, no, F06, no, F05. Let me see if I can get the right person here. Okay, so F05, now you really are on the air. We got a good solution from E05, but I want to see, is there anything even simpler?
Well, I was thinking of doing it by like intersection, like looking for a street segment with the correct street ID.
Okay.
And then going to the next node, and then looking for the same street ID that you didn't just come from. And then doing that until you can't anymore.
Oh, okay, so good idea. So you're saying you're going to go through all the intersections, right? Is that correct? And for each intersection, you're going to ask what street segments are connected to me. And I didn't show them up here, but there are API functions to do that, I think. Actually, that one I'm not sure we have that API function. But your idea is go through all these intersections, and if an intersection can get what street segments are connected to me, then you could use that to find those street segments, ask if they're part of the right street.
Yeah.
Okay? Yeah, it's a good idea. I believe we don't have the function that, no, actually we do have that. So you're right, that'll actually, that's a good solution. It's not the one that I have up here, but that would work fine. Okay, so good answer. And we've got A09. Let's see, what do you think? What do you think?
I just have a question though, So like the STL library, we have like members of these classes like vectors and maps. And,
Yeah.
and they, like we have like resources that tells us what these member functions, what they do. For the API, do we have something similar like because there's member functions in these classes that are useful in the high level and low level?
So the API is documented in the header file. We didn't make the API into member functions. We made it more as an API where it's like more what are called global functions. They're like C-style functions. It's the same. We give you a bunch of functions. They're all clearly documented.
And we have like a doc. So we mean documented as we know what all the names of these functions and what they all do.
Yeah, that's the header file. So that is the purpose of a header file,
Okay.
right? And that's what Streets Database API.h gives you. What are all the functions you can call? How do you call them? What do they do? Okay, so actually we've got a couple of good solutions here. So both ece297 and F05, those solutions will work. I'm going to show you one that's slightly different. Okay, so, and it'll also work, okay? So here's my solution. I make an empty vector. This is my answer, okay? So I'm supposed to return a vector of intersection IDs. So first I need to make the vector as a temporary variable, and I'm going to return it. Okay, so my first line and my last line are kind of obvious. Here's my result. Okay, now what do I have to do? As you just saw, there's not one answer only to this, but here's the way I did it. So I'm going to loop over all the street segments. So I can call get num street segments. So in Toronto, it's something like 190,000. So I get told there are 190,000 street segments in this city. They're numbered from 0 to 190,000 minus 1. I'm going to loop over all of them. And for every one of them, I can say, give me some information about it. And the information that's returned is a structure. So remember, a C++ structure is just a class with everything public. Okay, so this is a very simple class. It just groups together a few different data members to organize things. So I've got this street segment info now. And a street segment does know, it has this member street ID. This is all in the header file. So you look at a header file, you're going to find this. And basically I have to check, well, is that street ID 150? Well, is that street ID equal to the one that I've been asked to find all the intersections of? Say that I was asked to do this for street ID 150. If your street ID matches that, then I care about you. If your street ID doesn't match that, I don't care about you. Okay, if your street ID does match, what do? Well, I'm asked to find intersections. So I'm going to look at your from intersection, I'm going to look at your to intersection, and I'm going to check, do I already have these in my answer? So are they already in my vector? If they're already in my vector, I'm not going to do anything. If one of them or both of them are not in my vector, I'm going to push them into it. And after I've gone through all my street segments, I can return my answer. Okay, does everybody agree this will work? Do you see how it will work? Does it make sense? Okay, how fast is this? Like, what is the computational complexity of this? So I'm going to go to B11. So give me, okay, B11, you're on the air. Oh, I muted you again. Sorry, go ahead.
Is that O(n)?
Yeah, this is ON, okay? Where N is the number of street segments in the city, because I got a big for loop over it. Basically, the API calls we've given you are order 1. Okay, so we haven't intentionally made our API slow, but you are going to call our API n times. So this is going to be an order n answer. That's going to fail the speed tests, okay, because this particular function we said is high. But you're still going to pass all the functionality tests, so we still made good progress here. You cannot make this faster than order n using the APIs we've given you, because there is no way to just say, give me the information for this one street. We didn't organize the data that way. So this is as good as it gets, given the API we've given you. So let's go to, are you B12? B12, what do you think?
No, I just wanted to notice the fact that, is that supposed to say street there, where it says steep? Like, the missing R.
Which one?
The first for loop.
First for loop. Street segment, oh, this you mean?
Yeah.
You're saying that street is spelled with an R?
Yeah.
Okay, no, I was just questioning. You just spelled with an R. You caught me. I was seeing if I could get you to back down before I gave you a chocolate bar. I owe you a chocolate bar afterwards. Although I did make you, just by asking you that in that tone of voice, I made you briefly worried. Wait, maybe street doesn't have an R. It does. You got me. Okay, I'll fix it afterwards. Okay. So write this, past functionality. How would we make this faster? So what I told you that there's no way to call our functions that is going to be noticeably faster than this, right? We've got 2 other solutions from other teams, but if you go through those solutions, you will find they also have a for loop in them, right? They're also order n. There's no way around it. So what are you going to do when you pass functionality, you fail performance? What is your solution now? And it's going to be more complicated. What is the basic idea? You're going to have to store some data. Okay, so this was not the fastest possible solution. The fastest possible solution, well, let's say Yonge Street has a certain number of intersections on it. If we had just pre-computed that answer in load map, we could just return it. And that is an order number of the intersections on the street. And that's a much smaller number. Typical street might have maybe dozens of intersections on it. It's not that long. It's far less than 190,000 intersections in Toronto. So, or 190,000 street segments and maybe 200,000 intersections in Toronto. So this would be a lot faster. So to do it though, we have to store data in load map. Okay, you don't know what our tests are going to ask you. Like I told you we're asking about street 150, which let's say that's Yonge Street. We're actually going to ask you about a whole bunch of streets, different indices. And we'll ask some in the public tests. We also have private tests that will run in your submitted code, which will ask you questions that are essentially the same, but with different IDs to make sure you didn't hard code things. So you have to be able to answer this quickly for any street ID. So you're not going to store, you're going to have to store the data for every possible question we ask for this. Now, if you work out how much storage is that, it's not that bad. Okay, it's still only order n storage, so you can actually pre-compute the answer for any possible call of this function in load map, and you can do that quickly enough, and you can do it spatially efficiently enough that then your this routine, the routine that just answers the question, can just return that preloaded data. Okay? The code that you would write to preload the data will be very similar to this. So if you wrote this first, as I recommended, it's not wasted effort. You mostly move that to load map, and you make sure you do it for every intersection, and then this function becomes very simple. Okay, does that make sense to everybody? We're going to go through this in even more detail for one of the other functions in the tutorial, where we actually see exactly what code we write in load map to make this fast. Okay, so I told you that you load anything you want in load map, you answer questions, then you clean up. Don't forget to clean up. Okay, so we have tests where we run load map, then we use it, then we call close map, and we run valgrind to check if there are any memory leaks. So if you just lost some memory, you didn't properly clean it up, you'll fail the memory leak check. We also sometimes, we have tests that go load map, bunch of functions, close map, load map again, possibly of a different city, bunch of functions, close map. Students often fail those tests because they don't properly clean up. So don't assume that we only call load map once and you never have to clean it up. Make sure your close map undoes everything that your load map did, which isn't very hard, you just have to do it. Okay, so I told you that we are automatically checking for memory leaks, memory corruption in your program. Valgrind slows your program down by about 10x. So this often happens in testing. If we run your program through valgrind, the testing is more thorough, but it's slower, so we can't run as many test cases. So a good practice in testing is have some big test cases, but also have some small ones that you turn on a bunch of extra checking. And because they're small, you can tolerate it. So we do run this on a small map called St. Helena. Does anybody know what St. Helena is? This is not relevant to the course, but I can't resist. What is St. Helena famous for? Anybody know anything about this island? It's an island. You can see that. It's not very big. I think it's famous for being like the valgrind test for 297. It's on their tourist brochures. Now that you've written your 297 mapper, come see where your memory faults were coming from. It's not that. Okay, so it's one of the most isolated places on the Earth. It's the middle of the South Atlantic. And what do you do with a place that isolated? You exile Napoleon to it. So Napoleon conquered a good chunk of Europe, was defeated. They banished him to an island in the middle of the Mediterranean. He escaped, came back to France. He started a war again. They went, okay, no more Mediterranean for you. Middle of the South Atlantic. And he did not escape from that. And he bitterly resented being stuck on St. Helena. But you can now map out where did Napoleon spend his later days. Okay, so if you look at this, we pass load map the name of a map. And then when we call your functions, for example, find closest intersection, or the function I just showed you, we don't pass you anything else. Well, we just pass you a position. We pass you nothing else. So how am I going to answer these questions? In order to get data from load map into your function calls that are answering questions, your other M1 functions, you need a global variable because it's not, extra data is not being passed in. Okay, stuff that you might have loaded in load map. Okay, and you might have heard global variables are bad, right? So, and they are if you overuse them. So you don't want to basically go, I don't like writing parameters in my functions, so my functions just get everything from global variables. I mean, that's chaos. Your programs will not be maintainable. But almost all programs have some global variables. So for example, what do you think this is? Okay, so what kind of variable is that? That is how you output things in C, or input things in C++. Did you pass standard C into every function you ever wrote? You didn't, because it's a global variable. Okay, so the creators of C++ could have said, you have to pass C in and C out to every single function you ever write starting at main, but they decided that's madness. It's a global variable. Everybody can use it. So almost all programs have some global variables. This is a very reasonable use of global variables. You want the standard input, everybody wants it, make it global. Okay, so what you should do is be a responsible user of global variables. You want to limit their number. And how do you limit their number? Well, a good technique is to group related data into classes or structs. Structs are the same thing as classes, just all the members are public by default. So instead of having 20 global variables in load map, it would be nicer if you made a struct or a class, maybe you call it street graph, and you make member variables that are all the things you need to store, okay? It's really not functionally any different. It just looks cleaner. It avoids namespace pollution. It's easier for someone to understand. It's clear all these variables go together. Okay, so that's what I've done now. Load map and close map are loading up my global variable, and my other functions are just accessing it. Okay, so the other thing is we're going to use these global variables in a very disciplined way. Okay, so all of your functions in M1.h, except close map and load map, are just going to read these global variables. So they're going to look at them in order to answer questions more quickly. So it's like a database that they can leverage. The only place where we're going to change these global variables is in load map and close map. And this is a very disciplined use, right? You are creating truly global state. It's like a database I need for my whole program to be able to answer questions. Does that all make sense to everybody? Okay, so the other thing you're going to need in milestone 1 is a little bit of computational geometry. So you're going to notice that we're working with points on the surface of the Earth, and some of the questions we ask you require a little bit of vector geometry. One of the questions we ask you is about the area of a feature. And I told you that features are these polygons that describe things like ponds, lakes, forests, etc. Okay? So here there'll be multiple features. Like for example, there's a feature like this that is High Park. And it's a complicated polygon. What we give you is we tell you how many points are in the boundary of that polygon, and we tell you the points in order. And we guarantee that none of the polygons have holes in them. Okay? So they're all what are called simple polygons. For a polygon like that, does anybody know how would you find the area of a polygon like that? Because we ask you to find the area of a feature. Anybody know how you would find it? You know a formula for a triangle, you know a formula probably for a square. You probably don't know a formula for like something that has, maybe 106 points in some complicated shape. Okay, so F05, looks like you have an idea. What do you think?
Could you,
Whoops, let me make sure you're on. You are on, speak loudly.
could you somehow split the polygon into simple triangles and then calculate the area of each one of those triangles?
Okay, so that's a reasonable idea. So you're saying split it up into triangles, and we know how to do a triangle, so maybe we can split this up into all triangles. Yeah, and you could do that. However, the code, that's called tessellation, okay? Break something into a bunch of triangles. The code for that is pretty complicated, especially for polygons of the complexity we're going to give you. So good idea, but I'm not going to recommend you do it that way. Any other takers? B13, you have an idea?
You use cross product, like 3 adjacent points.
So you're saying use the cross product. You can't quite, I don't know how to do it with the cross product, but that's a good thought. You may find in some of this assignment and the next milestones that vector things like cross and dot product are useful. Let me show you, you can do this with numerical integration, okay? And that sounds hard, but it's not. So the reason I'm showing you this one is it might be scary if you don't think of this. Okay, so we give you the points in order. So let's say this is the very first point, point 0. And this is the second point, point 1. I can basically work out what is the area of the trapezoid. This is very simple code that goes from the y-axis out to this point, right? Just average these two x coordinates and multiply by the distance in y. That's very simple. And I can write a for loop. I can do that again. So I go on to the next 2 points, and I compute the area of this, okay? So I've gotten all that area. When I go down like this, let's see if I can get a different color here. Okay, so I've basically taken y2 minus y1 times x2 plus x1 over 2. So I took the average x multiplied by the difference in y. That's the area of that trapezoid. And that's adding area up. When I hit this point, now my y2 is actually below my y1. Okay, so I'm actually going to get y2 minus y1 is negative. What does that mean? It means I actually subtract the area of this. Okay, and down here I'll subtract the area of this, and then I'll keep going up the other side, and I will actually add in this area, and I'll add in this area. If you look at the result of that, you get the area of the polygon. This works for any polygon that doesn't have holes in it, and we won't give any polygons with holes in it. We don't guarantee an order, okay, so we don't guarantee the order is that way. Maybe the order was the other way, okay? We do guarantee